In this final video on section 9.3, we're going to talk about conditional probability. And so we're going to take, instead of probability of A and B equals probability of A times probability of B, that's the case when things are independent, when they don't have any influence on each other. Flipping a coin once, flipping a coin again, no influence. But we're going to use this other modification, probability of A and B is equal to the probability that A occurs times the probability of B occurs, given that A already occurred. So this is a dependent situation. So B's chance of happening, it's dependent on the fact that A already happened and is going to have an influence. That vertical line, we use the word given. Of course, we can take that second equation and we can divide both sides by the probability of A and solve for probability of B given A. The way I remember this formula is that the second letter in the given thing is also the denominator. And when we use this formula, the assumption is that event A has already in the past definitely occurred and happened. Here's a couple examples. If we have two urns, and for some reason historically mathematicians use urns instead of jars, but let's say we have two jars or urns, and they're called A and B. And inside urn A is 3 white marbles and 2 blue marbles. Inside urn B is 1 white marble, 1 blue marble. Okay, so what is the probability that we pick a white marble given that we definitely picked urn A? It's the probability we picked urn A given that we definitely picked a white marble. All right, well, the first question should be pretty obvious. We don't really need any fancy math for that. If you're telling me that we picked urn A, given that we picked urn A, the chance that we picked a white marble, well, there's 3 whites out of 5. It should be 3/5. And in fact, that's what it turns out to be using the formula. Probability I picked white and urn A. I'm going to assume that there's a 50-50 chance I pick one of these two urns. It's a random chance. So I have a 1 out of 2 chance of picking urn A and a 3 out of 5 chance of picking the white marble. Probability of A is a 1 out of 2 chance. I want you to notice that there's two things here, and you can put these two in either order. So I think you can, whatever order makes sense for you, like I'm saying, okay, urn A, pick that first, and then pick a marble out of it, even though it said it in the reverse here. But the second question is very counterintuitive. This is the one that'll be asked, of course. The probability, again, of picking urn A and a white marble, just like before. But this time, the probability of a white marble. Well, if I pick urn A and a white marble, there's the possibility there. Or I could pick urn B and a white marble. There's that possibility. And if I multiply by 20 over 20, there's the chance that I picked urn A, given that I have previously picked and I definitely got a white marble. All right, here's another situation, real life thing. So my daughter played soccer back in middle school, and there was 2 fathers who coached the team, and one was named Sam, one was named Joe, and Sam was there 60%, Joe 40% of the time. My daughter wanted to play goalie. When Sam was coach, she got to play goalie in practice, in games, about 50% of the time, but when Joe was there, only 30% of the time. So what's the probability that she plays goal, or she gets in the goal, given that Joe is coaching? Well, it's pretty obvious. It should be 30% of the time when Joe is coaching. Given that Joe is definitely coaching, she gets 30% of the time. So let's make sure the math works out. Goalie and Joe, multiplying those two over probability of Joe. Good. What's the probability that when I park my car and I come over to the game and I see, hey, she's playing in the goal, excellent. What's the probability that Joe is coaching, given that she is in the goal? This is counterintuitive. All right, so this time I have to do both probability of Joe and goal against. That's just like the top here. And again, we can put our numbers in the same order, whether these are backwards or forwards. But now, the denominator is probability she's in the goal. Well, there's 2 ways that could happen. And so often in these conditional probability problems, there'll be a more complicated denominator. How could she play goal? Well, Joe could be the coach, and she's playing goal. Or Sam could be the coach, and she's playing goal. Those could both occur. And so now, if I see her in the goal, there's a 28.57% chance that Joe is over there on the sideline. So in this question, we are just totally making up numbers here. But let's say 25% of students got the flu last winter. And of these who got the flu, 90% of them had a high temperature. The other ones had the flu but didn't have a high temperature for some reason. Of those that didn't have the flu, 8% of those ended up with a high temperature for some reason other than getting the flu. So what's the probability that you had the flu given that you had a high temperature? So you definitely had a high temperature. What was the chance you got the flu last winter if you were a student? So this is one event that's happening, picking this one person and asking this one question. So here's our formula, and the second thing goes in the denominator. Got the flu and got a high temperature over how's the likelihood that you would get a temperature? Well, you could have the flu and get the temperature, or you could not have the flu, which would be the rest of these people, which would be 75%, and 8% of them would have the high temperature as well. So we can see that if you have a high temperature, given that you have a high temperature, the chance or the probability that you have the flu last winter was about 79%. Some people and some math teachers like to do this same problem using what's called a tree diagram. And so we have a decision point. We could have you have the flu or you don't have the flu. Another decision point, now that you have the flu, you could have a high temperature or not. If you don't have the flu, you could have a high temperature or not. We have the various percentages are there. Now, so each of these strands means something and something else. We had the flu and you had a high temperature. Had the flu and didn't have a high temperature. There's our line for didn't, etc. And then we could put together our calculations very similarly. So what's the chance that you had the flu and a high temperature over the chance that you had a high temperature, which means you had the flu and a high temperature, or you didn't have the flu and you still had a high temperature, and that would get the exact same calculations. All right, here's another Venn diagram-ish kind of question. The probability of not A or B occurring, neither of those, is 0.6. Probability B, probability of A occurring given that B definitely occurred, is 0.5. Is this independent? And let's draw a Venn diagram. So independent, we said things are independent if the probability of A and B equals the probability of A times the probability of B. We rewrote that as probability of A times probability of B given A. And we said that that would be used for dependent situations. So the only way this is going to be independent is if this piece right here equals this piece right here. Okay, so firstly we can take, if it's not in A or B, then it's not in either of these circles here. It's outside of that. So 0.1 would go right here. Okay, now, probability that's in B is 0.5. In there has got to be 0.5. Could be in somewhere in there or in there. Probability of A given B. Well, we know this formula, that the probability of A given B is A and B over probability of B. We know probability of B is 0.5. We know that this answer needs to be 0.5. So we can figure out the A and B, which is in the middle right here. Once we've solved for probability of A and B, now we can put the remaining part of B over here. And now knowing that all of these have to add up to 100%, that's how we know this is here. Now the last question is, do these equal each other? Well, again, we know probability of B. We know the formula for this, B and A over probability of A. We know each of those parts. Probability of A is everything. Probability of B and A is in the middle here. And we can see that that's close, but not quite equal. And the last thing we need to talk about is expected value, which is usually abbreviated EV. So say you buy a raffle ticket for $2. 500 are sold. There's a $200 prize, $200 prizes, three $50 prizes. What is the expected value of this game or this event? And what expected value is this formula, sigma notation. You take the probability of a certain value times the value. You add those all up to find the expected value. So in this particular case, you have a 100% chance of spending or losing $2. Or in addition to that, or you have a 1 out of 500 chance of winning 200, 2 out of 500 chance of winning 100, and 3 out of 500 chance of getting $50 prize back. So if we add all those together, your probability as a decimal or a fraction times your value, sum them all up, and we get negative 0.9. And what that means is that if you played this raffle over and over and over again, many, many times the same exact situation, on average, you should expect that you would lose 90 cents every single time. Even though you'd get some big wins, on average, you would lose 90 cents. So if the expected value had come out to 0, that in that case, it's called a fair game. It's a break-even kind of situation. If it had come out to be positive, you should definitely play this raffle, because on average, you will be making money. So again, expected value is taking all the possibilities and stringing them together. Sometimes negative, sometimes 100% chance of negative. You're definitely spending the money, sometimes positive. And the expected value in this case is from the perspective of the person playing the game or playing the raffle. If we did this expected value from the perspective of whoever was selling the raffle tickets, then this would have been positive and these would have been negative, because in their perspective they'd be giving away the money and they would have a positive expected value. One last question we'll do is referring back to the counting section that we did, 9.1. Say I get 5 papers turned in with no names on them, and I randomly guess on whose these papers are based on when I look at my grade book and I see the 5 students that don't yet have a grade, so I just put names on the papers. What's the probability that I get them all wrong? So that would be the number of derangements. And that would be derangement, meaning that I don't have the right name on the right paper or the right number in the right place, over the total ways. So good ways, where they're all wrong, that's the good way, over the total ways. Remember that there was a formula that we used to figure out the number of derangements, where k went from 0 to the number of papers, in this case, that we have. And that would be the good ways, where I got them all wrong. And I would divide that by the total ways that I could put names on the papers. And I would use fundamental counting principle for that. I've got 5 choices for the first paper, and I put a name on it, and 4 choices for the next paper, etc. And here the n factorials cancel out, and I get 20%. So there's a 20% chance I'm going to get them all wrong.